This is the MCAT Intensive Review brought to you by In Time TV. I'm Dr. Ogan Gurel. We're in the Biological Sciences section, the Organic Chemistry subsection. The chapter is nitrogen-containing compounds, and the topic of this video clip is the amide bond. A PDF will pop up during the break, which you can print out, annotate, study during the course of the lecture video, as well as afterwards, of course.
You're welcome. Yay!
The amide bond. The amide bond, also known as the peptide bond, is extremely important in organic chemistry, and of course, by virtue of being the fundamental connecting block between amino acids and proteins, very important to biology as well. The amide bond is a combination of an amine plus a high-energy acyl derivative, which we'll describe shortly, which combines to form an amide. This amide has the unique properties of planarity, it's a plane, as well as stability. And these properties of planarity and stability account for the properties of the amide bond, and in particular, obviously, because the amide bond is a peptide bond. Let's look at first the properties of the amide bond, and then we'll talk about how the amide bond is created. The amide bond, or amide, is a carbonyl, carbon doubly bonded to oxygen, with an amine attached to it. And here we have the brackets indicating that this carbonyl amine complex, the amide, is in fact a resonance form. Resonance indicating that there is delocalization of the electrons among these three atoms, the oxygen, the carbon, and nitrogen. This is the first resonance form, which shows a doubly bonded oxygen. The second resonance form, which is the minor resonance form, this is the major one, this is minor but not insignificant, shows a doubly bonded carbon-nitrogen entity. And of course, to create that resonance form where the lone pair of the nitrogen comes down to form the double bond with the carbon, and the pi bond of the oxygen goes out to form an extra lone pair on the oxygen, creates this charge distribution or dipole, so that in an amide, the oxygen is actually slightly more negative than a normal carbonyl, and the nitrogen is slightly more positive than an amine. The other implication of this, as you can see, is that there is some double bond character to this carbon-nitrogen bond, which is very important, as we'll talk about very shortly. So the amide is, in fact, a resonance structure in which there's delocalization of electrons over the three atoms of the oxygen, the carbon, and the nitrogen. And this, of course, is the amide. This resonance of the amide or peptide bond results in two properties. Stability. Why is it stability? Because the carbon-nitrogen linkage, which is the actual amide linkage, is more energetically stable than a pure single bond. Not quite as much as a double bond, but more energetically stable than a single bond. It has what's called partial double bond character, and hence the carbon-nitrogen linkage is very stable relative to a single bond. That's important. Proteins being the actors, if you will, on the stage of life, where drugs bind to, where proteins can be used to turn on regulation. Proteins are part of muscles. Proteins add additional strength to bone, etc. Proteins do almost everything in life. They are relatively stable. The other aspect is double bonds, carbon-nitrogen double bonds, are planar. The pi bond is a planar bond, so that there is actually not only stability but limited flexibility around that bond. It can't rotate. The nitrogen and the oxygen can't rotate around each other. It's a planar configuration, carbon, nitrogen, etc. The sp2 hybridization of the nitrogen means that this is a relatively planar bond. In fact, it is a planar bond under physiological conditions, which means there's relatively limited flexibility to the protein. The protein can rotate around the single bonds around the amide linkage, so proteins actually do have flexibility, but they also have a certain rigidity, and that's extremely important because proteins are a combination of having a fixed structure but also some flexibility. So it actually has the best of both worlds. That fixed structure is very important because your muscles are made of proteins, and if they were completely flopping around, they wouldn't have the stability to actually perform the function of being muscle proteins. A hormone has a defined structure. You don't want it to be so loose and flexible that it doesn't have a defined enough structure to bind to its receptor and so forth. So the stability and planarity are consequences of this resonance, and they define two very important properties of the peptide bond, which determine two very important properties of proteins. Now let's look at how an amide is created. An amide is created through the combination of an amine with a high energy acyl derivative. An acyl derivative is a carbonyl plus an electronegative atom of this sort. You should, in your notes, it's shown a question. Why can't you create a amide from a amine and a carboxylic acid? And you should be able to answer that question, and you can find the answers on the website. But it's a thought experiment, thought question that you should answer. But instead of using an amine and a carboxylic acid, you have to use an amine and a high energy acyl derivative, such as one connected to a chlorine here. In biology, the high energy acyl derivative is actually connected to a tRNA as an ester. So this nitrogen has a lone pair, attacks the electrophilic carbon of that acyl derivative, and then the doubly bonded, the pi bonds in the double bond to the oxygen then go out to the oxygen, and you get a tetrahedral intermediate here. And that tetrahedral intermediate is actually has a separation of charge with unstable electrons on this oxygen, transiently there as an intermediate. Those electrons come down to push out the leaving group, which in this case is the chloride, and that proton transfer also occurs. So loss of chloride, leaving group, and proton transfer, you lose hydrochloric acid, and you get the amide. Here's the amide with the oxygen, the carbon, and the nitrogen. Again, the central idea is you cannot form an amide from the reaction of an amine and a carboxylic acid. Instead, you need an amine plus a high energy acyl derivative, such as we see here. And that, through these sequence of steps, forms the amide. So in summary, the amide bond is extremely important. It is created from the combination of an amine plus a high energy acyl derivative. The amide is also very important because it has the properties, because of resonance, stabilization or delocalization, molecular orbital delocalization, has the properties of stability and planarity. These very important properties ultimately determine key features of proteins that make life possible. This concludes the video clip on the amide bond.